Hi, Dr. Azumi.
Did he hear you? Oh, left.
Hello.
Maybe, did he hear you? I think
Yes.
he's on the road as well. Maybe connection also stabilized back.
Yeah.
Hello.
Hello. Hey, Dr. Azumi, how are you?
Yeah, fine. I'm good. Sorry, Prof. The line is not so good. I'm actually traveling. Yeah, traveling now to Penang. Yeah.
I see. I can hear the car sound. I know you are traveling.
Okay, thanks. Anyway, enjoy the talk.
Sure, thank you.
Okay, right.
Thanks for the invitation.
Yes. I tried to join for a while. Probably. Let's see.
No problem.
Okay. Thanks, Prof. Carry on. Thanks.
Okay, thank you. Thanks, Dr. Azumi.
Yeah.
Prof, can we start now? I think you already reached like 30 people. Dr. Jack, can we start?
Sure.
Yeah, sure.
Okay.
If whenever Prof Lim is ready.
I'm ready anytime.
All right. Always ready. Yeah.
Always ready. Ever ready.
Ever ready. Okay. So we're going to start our webinar just in a few seconds. Okay. I think we almost reached like 30 people. I think okay, right? All right. So I'm going to start the webinar now. Okay. Assalamualaikum and very good afternoon, especially to our respectful, our honorable guest today. We have Professor Dr. Lim Eng Hock from Universiti Tunku Abdul Rahman. Our respectful Dean, Associate Professor Dr. Azrami Abdul Hadi. And we also have here Dr. Sopin Jack, Head Center of Excellence, COE, Advanced Communication Engineering, or known as ACE. And to all my fellow friends, lecturers, and last but not least is to all my beloved students. Welcome to SCCE Research Knowledge Sharing Webinar Series 10. So this webinar is organized by School of Computer and Communications Engineering, Universiti Malaysia Perlis, in collaboration with IEEE Malaysia Antenna Propagations / Microwave Theory Technique / Electromagnetic Compatibility, or known as AP / MTT / EMC Joint Chapter, IEEE UNIMAP Student Branch, and Advanced Communication Engineering ACE Center of Excellence. Before we start this webinar, I have a few announcements to make for the audience. Don't forget to fill up the attendance form. You may find the Google Forms at the chat box, because we're going to give you the e-certificate based on the attendance form. You will get the e-certificates via email. And towards the end of our sessions, there will be also an evaluation forms. I would like to seek cooperation from all the audience to fill up these evaluation forms so that we can improve this webinar for the next sessions. And before that, I would like to ask everybody to turn on their computer because we're going to take a group photo first before we start this webinar. Is it okay? Okay, tak? I think everyone is ready. We're going to take a group photo for a while. So perhaps you guys can turn on your video cam just for a while. Okay. I can see we have Cik Muhammad Noor here. You may turn on your computer. Then we have Dr. Ombiling. So our photographer today will be Dr. Nuramina. I can't.
Okay, everyone's ready? Do we have a photo? Okay.
Ready.
Okay, 1, 2, 3. Are you okay, boss? Okay. Okay, one again. Okay, once again, 1, 2, 3.
Okay. Right, thank you, Dr. Nuramina. We will share the group photo later at the FB SCCE Unimap as well as ACE Facebook. Okay, before we start this webinar, I would like to introduce to you guys a little bit about our speaker today. Okay, so Professor Hock was born in Selangor, Malaysia. He received his bachelor's science in electrical engineering from National Taiwan Ocean University, master engineering in electrical and electronic engineering from Nanyang Technological University, and PhD in electronic engineering from City University of Hong Kong. He served as the associate editor of the IEEE Transactions of Antennas and Propagations from 2013 until 2016. Currently, he is a professor at Universiti Tunku Abdul Rahman, where he is serving as a chairperson of the Center for Communication System and Network. He is the founding chair of the IEEE Council on Rfid Malaysia chapter and the IEEE Malaysia Distinguished Lecturers for 2019 until 2020. His current research interests include RFID antennas, reflector arrays/transmitter arrays, and multifunctional antennas. So without further ado, I would like to welcome our honorable guest today, Professor Dr. Lim Eng Hock, to present his webinar. Please welcome, Prof.
Okay, thanks, Dr. Sharatu. Okay, thanks, Dr. Arizmi, and thanks, Dr. Pinjek So, for inviting me to give this talk. Okay, I would like to share my screen now, right? Okay. Okay, can you see my PPT?
Yes.
Okay,
Can
good,
see your
excellent. One
PPT.
second, right? Let me. I can't see, right? Okay, okay. So here, today I'm sharing with you, right, my research on miniature UHF tech antennas for on-matter application. Of course, right. My name is Lim Eng Hock, right? I am teaching at Universiti Tunku Rahman, and of course, right. And we move on. So okay, so this is the location of Sungai Long. Actually, right, this is my office building. It is here, right? And of course, right, this is our city campus of Utah. And actually, right, it is about 180 kilometers away. We have another campus called in Kampa, right? So here, right, and of course, this shows you the faculties in our Kampa campus. You can see that quite a number of beautiful buildings here, right? Okay, and of course, right, I'm here. I'm at the Faculty of Engineering and Science, right? The Conchen Faculty of Engineering and Science. And of course, right, in my building, there are still also other faculties. They are sharing the same building here. Okay, so today, without further delay, I would like to share with you my research on the on-matter UHF I5d Tech antennas, right? So I think many of you are not in this field, right? So that right, I will introduce the background of this field, right? Before I start it off. And of course, right, I will go through some introduction on the UHF tech antennas, the overall introduction, right? And I will bring up also the onator UHF I5d tech antennas, right? Which I will tell you what are the design concerns and consideration that you have to take care of. And of course, right, once you are designing it, you need to measure and characterize it, right? Over here, I will tell you, right, what are the important parameters, right? And of course, right, in my PPT here, I have a lot of equation, right? But today, I can't go through those equations. I will just tell you the important points, right? Because I only have 1 hour. And finally, right, I will go through with you some of our design examples. So, okay, so we start off with the introduction and also background, right? So that for sure, right, RFID is a technology that employs, right, EM wave to track, to track items, right, or to track objects. And of course, right, what is the advantage? I think the main advantage is that, right, the tags can be tracked, right, even they are placed, right, several feet away. Even, right, they are not in the direct line of sight, right, of the reader antenna, right? And this feature is very different from those conventional barcode. Okay, and we move on, right? So, and of course, right, over the past years, and this technology, right, has been developing very, very rapidly, right? And it has been, it has been applied in many fields, right? In fact, right, not only overseas, actually, right, my group is also working with quite a lot of companies in Malaysia, right, including Toklev, right, and also, right, free scale like SAG, like quite a number of like MDT, a number of companies, right? I'm working with them, right? So usually, right, we are designing the antenna solution, right? And they will be providing the embedded system solution. And of course, right, I think on our route here, we can see a lot of RFID nowadays, right? Because the RFID tech, right, has been introduced into our tolling system. Okay, now here, and of course, right, here are the advantages of the I5d technology, right? I think this is a very important feature, right? You can read data without visual access, right? This one is one of the plus. Unlike the barcode, right? Barcode, if you do not put the bar, under the reader, right? It cannot read, right? But RFID, right? It can read anyway, right? And of course, right, you are able, right, to read data from moving objects. I think this is also a very distinct advantage. And of course, right, you, depending on the technology, right, later on I will go through briefly, right, and RFID is able to read, right, from a few cm to 100 meter, right? And of course, because you are encoding, right, you are getting the data, right, into a much complicated way, right? You can also apply some security feature onto the data, right? Not only that, right, you are able to rewrite or write the data into the text anytime, right? And of course, right, this is one of the very obvious advantages that what it is able to read multiple texts at any one time, right? Depending on your reader, right? For example, right, if you have traveled to Hong Kong before, right, you should notice that, right, they don't use barcode. They put an RFID on your luggage, right? Actually, right, at the reader, right, let's say your luggage going through the conveyor, right, I think they can read 200 to 500 pieces of luggages at any one time, right? Depending on your readers and depending on your technology. And of course, right, but I think for this RFID, you have to design it, right, to suit the application. This is the key point, right? So here, right, and of course, right, when you are designing RFID, you have to design it, right, in several regulated bands, right? You please keep in mind, right? Let's say when you are applying your RFID technology in Malaysia, right? You have to follow, right? You have to design it in those spectrums which are approved by our MCMC, right? So most of the time, it is from there are three categories, right? The first one is the low frequency, right? This is in terms of maybe about 120 something K, right? We call it a low frequency. And of course, right, you have MF, right? This is a medium frequency, right? Which is the frequency is still very low here, right? And another one is a HF, high frequency. This one, right, is in the 13.56. This is a high frequency, right? And over here, right, this has been broadly used by our condo and office access card, mostly using this high frequency, right? And of course, for my research, I am focusing mainly on the UHF high frequency tech antennas, right? Why is it so? Because I'm doing research, right, for publishing papers also. So that, right, because this bandwidth, this band, it involves antenna. So my expertise is antenna, right? So easier for me to publish paper. And for this UHF, right, the regulated band is from 860 megahertz to about 960 megahertz, right? And of course, right, beyond that, right, although some people are proposing, right, 2.45 gigahertz, actually to date, right, this frequency is not approved yet, right, by the authority. So now here shows you, right, the global distribution, right, of the frequency spectrums for this I5d bands, right. I think we are pretty much quite close to Singapore, right, about 923 to 925 megahertz. And of course, right, I think in Malaysia also, some of the tags are designed to be in 866 to 869, right? And actually, right, this is following the European band. You can see that, right? The whole Euro, they are using 865 to 868, right? And we move on, right? So here shows you, here compares the features and advantages, right, and drawbacks of some of the different technologies, right? So I think the first one is LF, right? You can see that, right? This one is a typical LF tag. It is designed by winding this wire, right, to form an inductive coil, right? And of course, right, I think for some, let's say a pet, right, you are injecting this kind of tag into their body for identification, right? So what is the advantage of having so? And of course, right, this one is working at a lower frequency, right? It's not affected by water and metal. And of course, right, because you're winding, right, it contains some more expensive electronics. So that, right, it is more expensive, right? And because the frequency is low, right, it is easy to pick up noise from the environment. And of course, right, due to this low frequency again, right, your data transfer rate and also your read range are both shorter, right? Usually for such a tag, right, the read range is below 2 cm, right? So when you are moving up to a higher frequency band, right, 13.56, right? And again, right, you can see that, right, if you are opening up your office access card, right, even your smart tag card, you can see this coil inside. And of course, right, this is a design at 13.56 megahertz, right? So again, right, you see that it's using coilings. Coiling, it means that, right, it is applying the magnetic coupling mechanism, right? Because of that, right, it is less affected by water and metal, right? And of course, right, it is also, because the frequency has moved up higher, right, it is less affected by electrical noise. And of course, right, because of the use of higher frequency, right, the read range now is slightly longer, right? Usually, right, for a HF antenna, right, the read range is below 20 cm. Right, and of course, right, but when you are placing it on water or metal, right, it becomes slightly less effective, right? It's still working, but slightly less effective, right? Okay, now, if, of course, right, you can see that, right, for both LF and the HF, right, we are actually, right, using inductive, coupling mechanism, right, for achieving this kind of, sensing purpose. And when the frequency is going up to UHF, right, ultra high frequency, right, and of course, right, because of the use of higher frequency here, right, you are employing, you can see that, even you can see from the shape here, right, it looks like a dipole, right? In fact, dipole is the most frequently used antenna for this for UHF I5d, right? So for such a case, usually, right, the read range is larger than 3 meters, right? And of course, right, nowadays, right, there are a lot of technology. For example, right, you can make it on PET, you can even make it on paper, right? And you can produce them in a very inexpensive way, right? And of course, the cost is much lower because of the use of higher frequency, right? The data rate becomes much higher, right? And of course here, right, because this antenna is how to say, it's very sensitive to its surrounding, right? For example, if you are placing it near to water or metal, right, they can't work, right? And of course, right, you have to design your antenna really carefully in this band, right? I think because of this, right, so I am my research, right, is actually in here, right? We are finding out the best antenna structure for designing a different texts. Okay, here shows you some of the tech antennas that you can find in the market, right? And actually, right, 2 years back, right, I also worked with the WET department of Australia, right? We designed this one. And of course, right, this is just for consultancy purpose, right? And actually, right, designing such a tech, right, is not difficult because it is just how to say, inductive coupling, right? You quite the wire up, and it is able to work, right? And of course, right, when the frequency goes up in the high frequency, you are still using the loop. You are employing a loop, right, for achieving this sensing. And of course here, right, the size is still not so big, right? But how to say, but the read range is not so long, right? And when you are moving up to the UHF, these are some of the commercial texts that you can find outside. Let's say, for example, here, right, you can see that, right, actually, it's a dipole. This is also a dipole. This is also a dipole, right? And of course, right, this is just folding a dipole into a different shape and so on, right? So now here, because I believe that some of you are not from the background of I5d, right? So that here, I will, how to say, I will make a short introduction on the working principle of I5d, right? Basically, in I5d, right, surely you have a tag, right? A tag. This tag is holding the identity, right? And of course, right, you have a reader antenna here, right? So after the signal, you see that, right? Your reader antenna is sending some signal, right? RF signal to this tag, right? To wake it up. And of course, right, after the energy is sufficient to wake your tag up, right, it will send back the identity back to your reader antenna, right? And your antenna will send the data back to the reader. And later on, right, you can process it in your computer. And even you can use apply some IoT feature into that, right? So, and of course, right, in principle, right, for this I5d, you have a tag, right, which consists of a microchip, and also to store and process that information, right? And also, right, you have an antenna to receive radio frequency wave, right? Also here, you have a reader, right? Of course, reader itself is an antenna, right? Is connected to your reader here, right? So you can see that, right, when I was doing, actually, right, I was venturing into I5d, right, in 2014, about 6 years back, right? Before that, right, I wasn't doing I5d, right? So when I was doing I5d, right, I think my first challenge was this chip, right? This chip is very, very small. You can see that, right? Actually, it on an I5d, right, the larger part is your antenna. It's not a chip, right? The chip is very, very small. It is much smaller than a grain of sand, right? So you really need to have, how to say, soldering station with the right dispensing force, right? And hot plate, right? To place the chip on the antenna, right? Usually, right, the impedance of this chip, right, is in complex. For example, right, let's say if you are using, how to say, impinge 5, for example, Monza 5, right? Monza 5, for example, right? The real part could be maybe about 16 or 15, right? The imaginary part is minus J about 160, right? So that, right, you can see that, right, in order to match with this chip, right, you have to design your antenna, right, to have a complex impedance. I think this is a key point, right? If you are designing your antenna, right, using a 50 ohm convention, right, very sorry, right? I think the industry people, when they look at it, right, they will just, how to say, laugh at it, right? Because how to say, it is not for practical use, right? So please keep in mind, right, when you are designing an I5d tech antenna, the antenna impedance, it must be a complex number, right? So that it can achieve conjugate match with the chip impedance, right? Okay, now we come to the interaction of this UHF tech antennas, right? So, and of course, right, there are two types of techs, right? The first one is passive. Passive one is very cheap, right? It does not have any battery. And of course, right, for such a tech, right, it is, how to say, it's already very, very broadly used, right? Another type is active, right? Active, of course, right, it has a battery here. You can see that, right? So that, right, but for most of the active tags, just like your smart tag, right, it has a transceiver, it has a battery, right? And of course, right, you have to replace the battery from time to time, right? For the passive tag that you find outside, right, most of them, right, they don't have a battery, and the cost, right, is actually very, very low. On top of that, right, you can also classify the tags by using the technology, right? Some of the tag can be read only, right? You cannot rewrite them, right? But most of the text, right, you can write and how to say, and you can read and rewrite for many times, many times, right? Not only that, right, you can also save data, right? And you can also change the ID anytime, right? So here shows you, right, some of the commercial text that you can find outside, right? You can see that here, let's say for this tag, right, actually you can see that the very small dark dot here, right, this dot is actually the chip. This bigger size one, this is a dipole antenna, right? And of course, right, over here, you can see a few more, right? Most of them are designed using dipole antennas. Even here, right, actually it's a dipole antenna, right? So, and of course, right, so now we come to the design requirements of the UHF tag antenna, right? So I think for most of the cases, you have to design your tag, right, such that, right, it is easy to manufacture, right? If you're working with industry, right? And of course, right, it must be very low in profile, right? Usually, right, the profile shouldn't be more than 5 mm. I think it's a key point, right? If your profile is too high, actually, you cannot use it practically, right? And of course, right, actually, for all the tags are electrically small, right? So that later on you will see, right, most of the realized gain are in the negative zone, right? Because how to say, the tags are actually an electrically small device, right? And of course, right, you must make your tag light in weight to be able to achieve a very long read distance and so on, right? And of course, right, in recent years, right, we have also published quite a number of papers on the platform insensitive tag. Okay, and we move on, right? So here shows you, right, and when you are designing a UHF, right, tag, right, actually, right, it involves, right, making trade-off in between antenna size, read distance, and also the material cost, right? So here, so usually, right, as we all learn, right, the antenna size is how to say, proportional to the radiation efficiency, right? It means that, right, when your antenna is made larger, right, usually, right, your radiation efficiency, it can be enhanced significantly, right? But unfortunately, right, you can't do so, right? Because if your antenna size is too large, right, it can't be used, right? And of course, right, I think the main challenge here is what? Actually, right, the working frequency of your tag is very low, right? It's about 860 to 960 or less than 1 gig, right? If you are converting it to wavelengths, right, this wavelength is very large. So that, right, you really have to design it small, right, such that, right, it can be used at such a low frequency, right? And of course, this is the first criteria, right? You have to how to say, compromise your antenna size in order to have how to say, small in order to be usable, right? Not only that, right, you also know that, right, okay, for a tag, the most important feature is the read distance, right? And of course, right, this read distance, it can be improved, right, by how to say, by having a better impedance matching in between the tag and the chip, right? So, and of course, right, another way of increasing the how to say, read distance if is to increase the radiation efficiency. In this case, right, you have to increase the size, but unfortunately, right, you can't do so. You can do so, right? So how to say, you have to struggle in between antenna size and read distance, right? It means that, right, when your antenna size is large, your read distance is good, right? But unfortunately, it can't be used, right? But when your antenna size is small, right, the read distance becomes poorer. But how to improve it, right? This becomes a question, right? And finally, right, it is the material cost, right? So usually, right, when you are designing a tech antenna, right, you can't use external matching circuit, right? And of course, right, for commercial purpose, you also can't really use the multi-layer structure, right? Because it increases the cost overall, right? Okay, now here we move to our topic of on-meter UHF tech antenna, right? Actually, this is my the core of my research work, right? Okay, you can see that, right? Most of the commercial tech, right, they are designed using different types of dipole antennas, right? And of course, right, when you use them on other objects for nanometer, right, they can achieve a very good and a very excellent far field radiation, right, and a very good read distance. But how to say? But you see, right? Let's say you buy a tech from outside, for example, right? Just now you saw a tech here. If you don't believe me, right, or your smart tech, right? Your smart tech looks like this one, right? You put it, if you don't believe me, you put it on the metal surface, right? You'll find out, right? The read range will reduce, right? Maybe from meters, right, to zero, or even less than 1 cm, right? The reason why is very, very simple, right? Because you see, right? Let's say this is for example, right? If this is the current on your generated by your antenna, right? If you are placing your antenna, right, near to the metal surface, right, this current, right, electric current, it will induce an image here, right? And this image current is in the opposite, right? And of course, right, since they are cancelling out each other, right, it is causing the radiation efficiency to degrade significantly, right? There's a reason why when you are placing your dipole antenna on a metal surface, right, it can't work. It can't work, right? So here now, right? So of course, right, they are in the market, right? There are also many types of how to say metallic how to say on metal tech antennas, right? That can be used on metal, right? For most of the cases, right, the read range will be around 3 to 4 meters, for example, right? And for most of the antenna structure, they will employ a metallic ground plane, or to how to say, to electromagnetically, right, isolate the antenna from the backing conductor surface, right? So that, right, in recent years also, right, we I think a lot of people are trying, right, to use this AMC, or this how to say, or EBG structure to isolate the radiator from the backing method, right? I think just early this year, right, my I think Dr. Nabila Rfid is also I saw her name just now, right? Is also here. She has designed a tech, right, which with an embedded how to say AMC, right? Actually, after Dr. Nabila published this paper, right, quite a lot of company they either call me or wrote to me, right, to tell me, right, oh, this feature is very, very interesting, right? It's very useful, right? I think you can see, right, before Dr. Nabila published a paper, right, all of the tech antennas with AMC, right, or EBG are all very large. But now we are making it, right, to become less than 30 mm by 30 mm, right, or 3 cm by 3 cm. Okay, now here, and here shows you some of the antenna structure for the on metal text, right? So I think microstrip, of course, right, in the maybe in early 90s, right, you will see quite a lot of paper proposing, right, the application of microstrip patch for designing on metal tech antenna, right? But you look at those antenna, right, usually, right, their size will be like 20 cm, 25 cm, 30 cm, right? This size is simply too huge to be used for real application, right? Not only that, right? So that some other people also insert a ground underneath a dipole, right? To design a grounded dipole. And of course, right? Usually for such tech antenna, right? The real part, the how to say, the radiation resistance, right, is very, very low. Not only that, right? So in order to reduce the size, some people are also, right, employing different types of pitch antenna, right? And they modify it to become the PIFA, right? It means that, right, they are incorporating vias, right, to miniaturize the size significantly. But how to say? But the problem is that, right, when you are placing via into your design, right, the problem is simple. You will find out, right, your antenna will become extremely sensitive to your via location, right? In this case, right, it is very difficult to be tuned also, right? So of course, right, if it is very difficult to be tuned, you cannot use it, right? So, and of course, right, in recent years, people have explored, right, the use of EBG and AMC structure for designing, right, this tech antennas, right? And of course, right, usually, right, for those EBG and AMC structure, right, of course, right, if you want to apply such structure, right, you have to be very careful, right? Please avoid using vias in your EBG or AMC, right? If you have employed a lot of vias, right, actually, right, the antenna design is not useful, right? So not only that, right, some other people are also inserting, right, high permittivity spacer to how to say, to isolate the radiator from the backing metal, right? In such a case, right, you have to know that, right, high permittivity, how to say, dielectric, such like ceramic, right, is very expensive, right, to be made. Okay, now we come to this the how to say, the tech characterization, right? Of course, right, in order to measure, to see the performances of a tech, right, you need to measure it, right? So usually, right, the measurement is conducted by using two ways, right? For the first one, okay, maybe we look at our setting first on the next page, right? So that, let's say this is your tag, and your tag is connected to a microchip, right? It means that this is your tag antenna, and this is your microchip. And let's say, right, this is your reader antenna, and this is your reader, right? So that this is your distance, your read distance, right? So in method number one, you are keeping, right? Okay, it means that, right, your reader is sending a fixed transmitter power PTX, right? And you are varying the D, right, to find out the maximum read distance that it can achieve, right? This is the method number one, right? But if you are doing so, right, it means that, right, you have to vary this one manually, and it's a kind of inconvenient, right? So that, right, most of the people are adopting, right, this method too. It means that here, right, you are fixing the distance in between the reader and also the tag, right? But you are stepping up the PTX, right, the power from the reader, right, slowly until your tag is readable, right? So that, in that case, right, you can calculate the read distance from there, right? Actually, you fix the distance and you are stepping up the power, right, the transmitter power, until you can detect this tag physically, right? And of course, and this is how to say, and actually there's a commercial system for measuring this how to say, this system, right? And this is the Voventic performance system. Actually, we have one here at Utah, right? And over here, right, let's say, right, if you are measuring on metal, right, usually, right, we are using a copper tape. You can see that, right, this one, right, we are placing the antenna here, and we have a reader antenna, right? And actually, right, this performance system, it is employing, right, the second method for how to say, for calculating the read distance. And of course, right, I think the whole theory of the read distance calculation, right, is based on a Friis transmission equation, right? And of course, right, I'm not going to go through the whole theory here, right? But here, I'm telling you, right, what are the important parameters, right? If you're interested in the theory, right, you can find it out from any of my papers, right? So here, right, you can see that, right, usually, right, for a tag antenna, you are looking at the tag sensitivity, P-tag, right? And this is very important, right? And how to say, actually, right, it can be calculated here. And this is what? This is how to say, this is the power. Actually, you can see the equation here, right? It is actually a Friis transmission equation, right? Not only that, right, you are also looking at the tech antenna gain and also the power transfer coefficient of your tech, right? This are very, very important, right? And of course, right, in the deformance system, you can measure the realized gain, right? Realized gain is defined to be what? To be a tau multiplied by your G-tech here, right? So that, right, so these are some of the important parameters that that are important for characterizing attack, right? You can look at the realized gain in this way. It's just like our antenna gain, right? But it has incorporated the matching condition, right, and so on, right? So that, right, ultimately, right, after obtaining all those important parameters, right, you can use it. You can use it, right, to estimate your maximum activation distance, right, or the maximum read distance, which is your Rmax here, right? And of course, right, actually the whole theory, right, is is leveled up based on the Friis transmission equation, right? If you're interested, right, you can pull out my paper, any of my paper, right, to read it, and you will see it, right? So now we move on to our design example, right? So here I'm sharing with you quite a few design examples, right? So the first one is this serrated page, right? So that you can see that, right, before being folded, right, actually, right, it appears in this way, and this is your ground, and this is your radiator, right? Now you are placing this serration, right, on your radiator, right, in order, right, to lengthen the current path. Of course, right, here, right, I have a matching stub here, right, to reduce the frequency, right? And of course, right, I'm folding it, wrapping it around a foam material, right? So that, right, the size becomes too small, right? The size here is about 3 cm by 3 cm, right? The thickness is about 1.6 mm. 1.6 mm, right? So now, I'm sorry, it's about 3 mm, I'm sorry, about 3 mm, right? So, right, you can see that, right, here, we are introducing, right, a new type of flexible form, right, to design the tag, right? And of course, right, because of the folding feature, it does not need any, via, right? Because the shorting path is simply on the sidewall, right? And of course, right, you are placing your chip on the sidewall to avoid, right, being easily hit by external objects, right? And of course, here, right, you are using this serrated edge to to reduce the frequency down, right? Okay, we look at and of course, right, we first published this, right, in the TAP in 2017, right? So you look at it, right? So here on this slide, it is giving you the design parameters, right? So, and the size is what? Footprint is 30 mm by 30 mm, right? The thickness is 3 mm. And it's working at 915, right? Actually, here, right, I have to tell you that, right, you noted that, right? You see my marker here? You have a loop here. Actually, this loop is very significant for bringing down the frequency, right? If you don't believe me, right, let's say you just put your chip here without this stuff, right, you'll find out, right, the operating frequency of this tag, right, is at 4 gigahertz, right? So that, right, so I think designing a tag antenna, this is the key point, right? You must find out the tuning mechanism to bring down the frequency effectively, right? So here shows you some of the design parameter, right? And we are using one type of polystyrene form here, right? Called we are making this this antenna. You can see even from the previous page, right? We are making this on a PET material, right? And here, right, after measuring, we are testing it by using this this deformance system, right? And of course, right, we are sticking it on at the center of a 20 cm by 20 cm copper plate, right? Okay, here shows you the read distance for different angle, right? You can see that, right, the maximum read distance is about 7 meter for this one, right? And of course, here in the deformance, we have also, since you see that, right, you have the maximum read range at about 40 degrees, right? So that now here we are measuring, right, the tag sensitivity, which is this curve, right, and also the realized gain, which are these two curves, right, for this tag, right? You'll find out, right, they are agreeing pretty well to the simulation, right? Your simulation is about 915, right? And your measurement, right, is about, slightly higher, right? And oh, sorry, your measurement here is slightly lower. You can see that, right? Your stimulation is here, right? And there is a discrepancy of about 2 dB. And now we are looking at the current distribution, right? You can see that, right? This because of the assistance of this duration, right? Your edge becomes longer. You can see that, right? Current is actually, right, circulating here, right? And because of this, right, you can use this duration to fine tune the frequency of your tech antenna, right? And of course, right, here shows you the electric field in between the top page and also the bottom page, right? And of course, right, we are also, since although we design it for metal, right, we are also measuring it, right, for different dielectrics here, right, for different dielectric materials here. And you can see that, right, in general, right, the read range becomes lower and the frequency is distributing in a range here, right? Okay, now here, and of course, right, at that time, we compare our how to say tech to a numbers of other techs, right? We found out, right, our tech was actually quite competitive, right? Most importantly, right, you can see that, right, the cost of such a tech, right, is actually very, very small, very, very small, right? Okay, now here we are moving to the next structure, right? This structure is designed using a dipolar pitch, right? The previous one, it was just a shorter pitch, right? Now here is a dipolar pitch, right? And of course, right, you can see that, right, we are introducing a new type of dipolar pitch for designing a UHF tech antenna, right? So, and of course, right, you're looking at this shape, right, it's difficult to comprehend, right? But I show you on this page. Let's say, right, if you are designing it from here, right, it is very obvious, right? Let's say you can just start with a straight slot. This is shorting stub. Behind it, right, there is a ground underneath, right? So that, right, you can see that, right? Okay, now I'm wrapping my this PET again around a soft material, right? And of course, right, you'll find out, right, this tag is much larger, and we have introduced in this how to say this notches, right, for lowering the frequency, and also this U-shaped stub for U-shaped slots for lowering, for fine tuning, right, the frequency. So here shows you the design parameter, right? You can see that now the footprint is even smaller, and also, right, the profile is even lower, right? And of course, here you can see that, right? Okay, it is designing for the frequency of 915 megahertz. Now we are using another type of material, right? As the substrate. So here, right, the SLR for the form, right, which I will show later, right, is about 1.06. So here, many people told me, right, designing a tag is not difficult. You just cut, right? When you cut, how to say, the current path will become longer, right? Then, right, you can design it at a very low frequency, right? Actually, it's not so, right? You look at it, right? Okay, now I show you, right? You really have to cut it carefully, right? Let's say we start this design from a straight slot here, right? And of course, right, right, you saw that, right? For my previous design, for my design here, right, I am mindering it in this way, right, in order to get around this low frequency, right? But of course, right, to compare, to use other technique, right, to show that, right, our technique here is good, right, we compare it with other techniques. For example, here, let's say, right, you can see that, right, you can also cut in the vertical direction, right? You cut a lot. You see, you cut, right? Of course, right, the frequency can also move down. This is your structure A. You look at the structure A. Structure A is here, right? Yes, the frequency is moving down, but doing so will also cause your Q factor to reduce significantly, right? You can see that, right? Okay, yes, the frequency has moved down to about 1.07 something gigahertz, right? But the key point, right, the realized gain has also reduced to about minus 14 dB, right? So here, right, this case, right, the read range is simply too poor, right? And of course, right, let's say, what if now we cut this at the center, right? You cut it at the center, and you see, this is our structure B, right? You can see that if you do that, right, yes, the frequency can go down, right? But again, right, you can see that, right, but the, how to say, the go down trend, the, how to say, is still too high. even it can go down here, right? 1.8, right? It's still too high to be able to be useful, right? For this UHF tag, right? If you cut it further a lot, right? Yes, it will go down slightly, but you'll find out, right? The realized gain becomes very, very poor, right? Not only that, right? Again, right? If you are introducing this, how to say, this serpented slot on the page, right? If you do so, yes, it will come down. You can see this our structure C, right? It will come down to here. But again, right, you see, right, even about at the frequency of about 1.3 something, right, the realized gain is already very, very poor, right? And we move on, right? And of course, right, we are simulating it, and we have simulated it and measured it, right? And we found out that, right, the simulated how to say realized gain is quite close to the measure counterpart and so on, right? And it's quite close here, right? So here we also study the effect of the Minder slot here, right? You'll find out, right, the inclusion of the Minder slot at the center, right, has how to say has increased the current path, right? And it does not decrease the how to say the Q factor so much, so that, right, you can see that, right, for this case, right, the resistance is still very, very good, right? And of course, right, we have also tested it on a different how to say metallic object, right, for practical scenario experimentation, right? You'll find out that, right, the frequency here, right, is very, very stable. And of course, right, we compare it, right? And of course, right, for such a footprint, right, the achievable resistance is considered quite good here, right? Okay, now we move on to another folded dipole antenna, right? Of course, right, this one is the chip, right? The photo of your chip, right? This are the bonding pads, right? If I show this one, right, you don't know what it is, right? But I show you the one on the next page, you know, right? So actually, right, what it's doing here, it is folding up the radiation page to enclose this how to say this matching loop, right? So after folding it up, you are getting a very complex structure, right? And a diameter is 31 mm here. And of course, right here are the design parameters. And we first published it, right, in 2017, right? Also in the tab, right? So here, and of course, right, we place it inside the anechoic chamber, and we have measured the pattern, the real patterns, right? So you can find out, right, no matter in free space or in the metal plate, right, the frequency here is very, very stable, right? It's about, you can see that, right? Let's say in free space, it's about 5.2, right, meter. When it's placed on metal, right, it becomes slightly lower, right, which is about 3 meter and so on, right? Sorry, right, 1.8 meter, right? Okay, here shows you, right, the surface current on your tag, right? You can find out, right, these two arms actually, right, they are forming, right, two very inductive stuff for bringing down resonant frequency, right? Actually, your radiation pitch are actually this pitch and this pitch, right? So, and of course, right, we also study the current distribution for in free space and on metal, right? So, of course, right, we have measured it for different types of metal objects, right? And also for different types of dielectrics, right? Containers. We found out, right, you see the right, no matter what is your how to say baking object, right? In principle, the frequency is very, very stable. It's very, very stable, right? Okay, now, right, this comes to my final config, right, that I'm sharing here, right? Actually, this config, right, we are trying to implement, right, an omnidirectional planar tag antenna, right? I think we are the first one in the world to achieve this, right? Okay, I tell you, right, the working principle of this antenna, right, it's very simple. Actually, right, you see that, right, on the top here, you have a patch, right? Actually, right, this patch is not a radiator, right? The radiator is actually the surrounding here, the surrounding. You see my marker here, the surrounding, right? And of course, right, this is a small loop here with the chip crossing it. It is functioning, right, as an exciter, right? And of course, here you see, right? So when we here you have two shorting stub, right? So because you have two shorting stub, magnetic field, right, is forming forming around the stub here, right? So you look at the how to say, the magnetic field distribution. This one we have simulated the magnetic field, right? You can see that, right? It's what? Okay, the magnetic field is curling around it, right? It looks like how to say, a vertical how to say, electric dipole, right? But in fact, this is a planar structure, right? I think we are the first one in the world to do that, right? Before that, nobody did it before, right? Because, right, for this tag, we have also measured the input impedance, right? And we are comparing it with the simulation, right? And we have also measured the how to say, the resistance, right here. So now here, you see, right? You look at the resistance, right? It is really a beautiful butterfly, right? Which is an omnidirectional antenna, right? You can find, right, in the publication domain, right, in the open literature, right? I think very few omnidirectional tech antenna have been published. And of course, right, for Pana one, right, I think our group here have published 2. I think this may be the only two, right? Okay, here, and not only that, right? So we move on, right? In my group, right, we are also active, how to say, doing a lot of antenna structure, right? I think on average every year, right, we try to publish about 10 TAP, right? About 20 Q1 journal in this how to say, I5d and sensor, right? So here are some of the antenna structure. This all are published in the TAP. Right, and of course, right, this one is also published in the TAP, right? Here we are employing how to say, coplanar structure, and over here, right, this one is actually a compact orientation insensitive dipole patch, right? This one is also available in the how to say, in the public domain, right? And here, right, we have not only, you see all these are silverish, right? Actually, this aluminum. We are also using a lot of copper on polyamide, right? Polyamide to design the tech antenna, right? And of course, yeah, this one is also published in the TAP, right? The read range of this one is very good, right? It's 14.5 meter, right? It was published by my PhD student, right? And of course, here, this tech you saw before. And of course, right, not only that, right, we have also published a long series of how to say, of tech antennas every year. And of course, right, in principle, here, right, for this talk, all the configuration here, we are using 2 types of substrate, right? The first one is or we call it PCB films, right? The first type is the PET, right? And here are the design parameters, right? And the second type is polyamide, right? And of course, right, here are the design parameters. Both of them are flexible, right? Not only that, right, we are using, right, such substrate also. For the first type, right, we are using the EcoStop PP2, right, PP2, and the epsilon is 1.03, right. And the second type is the thickness is slightly less, right, and of course, right, the rest are the same, right. Okay, and we move on, right? So you can see that, right? Designing an augmented UHF tag involves making strenuous trade-off in between antenna size, grid distance, and also material cost, right? And of course, right, if you want to have a longer grid distance, you have to sacrifice the antenna size, right? Smaller antenna, right, is alternable, right, by sacrificing the grid distance. But unfortunately, right, actually, right, you want small size and grid distance at the same time, right? If you work with industry, right, you sure have heard this from all the bosses, right? I don't care. I want the size to be small, right? At the same time, I want the read range to be also very far, right? Just like you want all, right? So here, right, and of course, right, so I think the main challenge of designing a tag is simple, right? You want to design a small antenna with some, right, effective tuning mechanism to bring down the operating frequency, right, while maintaining very good read range. I think this sentence, right, has summarized, right, what are to be done and what are the challenges for you, right, to design a tech antenna, right? So here, right, so here gives you I think, right, this one is I'm thinking of this way, right? So here, right, when you are designing an antenna, you want to a tech antenna, right? You want to achieve the footprint, small footprint, and also size, and also, right, you want to have a very long read distance at the same time, right? But unfortunately, right, you cannot have both, right? You must have a tuning mechanism to achieve how to say acceptable footprint and acceptable read range at the same time, right? So okay, so thanks for attending. Thanks for attention and thanks for attending my talk. Right, thank you very much.
Thank you very much, Prof, for a very informative presentations. It's a very good RFID antenna. Sorry, all right. I can't hear myself.
I can hear you.
Oh, sorry. Okay. So with that, I open up for any questions from members of the floor. Any question? Otherwise, I have a question.
Sure.
Prof, I have one question. Regarding the material of the RFID antenna, is it important? Because in normal microstrip we have FR4, Rogers. What about the material for this RFID tag?
Yeah, in fact, right, because the frequency is very low, and how to say, even you can use FR4. How to say, I think the loss tangent of FR4, right, is still acceptable at this low frequency. But the problem is that when you're using FR4, right, it's not flexible. It's rigid. I think the profile for FR4, right, is also pretty thick. I think it's about 1.4 mm. You can use FR4, but you need to use a thinner one. I think you can buy some 0.5 mm FR4, right? You can use that. But the key point, right, if you are using a very thin substrate, right, you'll find out, right, it's very difficult for you, right, to design some microstrip structure or P5 structure, because why? Your radiator, right, is too close to your ground, so that, right, the efficiency, right, won't be high.
Oh, okay.
Yeah.
So one more question, Prof.
Yeah, sure, no problem.
As for the RFID reader, because we are talking about more on the RFID tag, what about the RFID reader antenna? Is it the same design concept as the RFID tag, or it should be for the RFID reader antenna should have much more high gain? Because it need to read the RFID tag, isn't it?
Yeah. So RFID tag antenna, usually our tag antenna or the commercial tag antenna, right? I think maybe I talk about our measuring system first. In our measuring system, actually, right, the reader antenna, right, is made of a patch. It has ADVI. The size is larger because for a reader, right, the size is not a big constraint, right? It can be made larger. But for a tag antenna, right, it must be very, very small because it is to be tagged, right, on item. So usually, right, for the commercial, even for the commercial tag antenna, right, I think their reader, the gain is in the positive. Of course, right, it will be slightly larger. How to say? Because I opened up a commercial reader before, right? A small one, the handheld one, right? Actually, they are using the microstrip.
Oh, okay.
Yeah.
Right.
Yeah.
Any more questions from members on the floor? Ada apa-apa soalan? If you are a bit shy, you may write down your questions in the chat box so I can read out for you. I think I have one comment from Associate Professor Dr. Cheng. He said, "Hi, Prof. My senior is AP Dr. Lee Kim Yi, who served at Utah at Sungalong campus too. Please send my regards to him."
Sure. Dr. Lee, right, is also now doing FID and
Yeah. Oh, okay. Any more questions? Oh, there. Okay. From Dr. Isma Hayati. She wrote to ask, what are the basic guidelines to design the RFID? I noticed you didn't have the I noticed you didn't have the S11 result. So how to know in what range our RFID antenna works? Normally, for antenna, we start with basic formula of square, triangular, etc. And then we will refer to the S11 for the operating frequency. I think she would like to ask the guideline, how to design the RFID antenna.
Yeah. So again, right, I answer in this way. Actually, right, we were showing the input impedance. Actually, right, from the input impedance, you can get your how to say S11. And also, right, you have to keep in mind that, right, RFID, right, again, as I mentioned just now, right, designing a tech antenna, it is not a 50 ohm antenna. Right, because your chip itself has a complex impedance, so that, right, you have to make your antenna to have a complex impedance also. And of course, right, you can look at S11. It's not a problem. It's not a problem. And how to say, usually we start from there also. So we will come up with a structure and how to say, to see the S11. But we rather look at the S parameter, because it tells us how good our real part or the imaginary part, right, are matching to the chip. We need to know that.
Prof, I have a lot of questions.
Sure, no problem.
Is it the RFID tag antenna can be used more than one person, or it has its own ID? Each antenna has its own ID.
Yeah, each chip. Put it this way, the ID, right, is inside the chip.
Oh, okay.
Yeah.
So basically, the chips will determine how many person that can be used that can use the RFID. For example, let's say the RFID antenna, our toll nowadays, for the cars. Can the RFID tag the antenna tag can be used for different cars as well, or even specifically for that car?
No, let's say, right, of course, right, let's say you are placing your tag on another car, right? Actually, the reader, right, cannot recognize your car plate. It can only recognize the tag, right? It doesn't know. It will just let it go. Unless you are incorporating it, right, with some CCTV. You are capturing the car plate, yes.
Okay, all right.
But usually, right, let's say, right, you have a tag, right, you use it in car A. You can just move it to car B, right? Anyway.
Oh, okay, understood. Right, thank you, Prof. Okay, we have one more question from Dr. Muhammad Nasrun. I think Dr. Nasrun, they're going to meet you on next week, I guess. He would like to ask, Prof, does the locations of the chip is crucial, and how to determine the best location for it?
Actually, right, the location, right, because of course this is an RF structure. You place your chip, right, at different location, right, actually, right, and how to say, maybe you will affect it a lot. Maybe I show you, for most of the cases, right, to be practical, right, actually, right, you have to place your chip on anywhere on the top, right, because in the very beginning, right, you noted that, right, for this structure, we are placing the chip on the sidewall, right. Actually, when we presented this to industry, right, they have a lot of comments. They feel that, right, it's not convenient. Actually, right, if you are placing your chip on the sidewall, right, you see, right, when you're folding it, right, the chip can fall off easily. You please bear in mind, right, this is an aluminum patch. You cannot use solder, right? You cannot use a Hock gun, and you have to use how to say, some bonding material. And how to say, if you are folding it too much, it will fall off.
Oh, okay, right.
Yeah.
I hope it's answered the question, Dr. Nasrun. Any more question? Let me check. Let me check our YouTube. No questions at the YouTube. Okay, I have one question.
Sure.
This person asks, is it a chip is irreducible? What does it mean? Erasable. Oh, okay. This chip is erasable?
Yes. You mean that the data is erasable and rewritable, right? Right? Yes. For those rewritable chip tag, right? Actually, the chip, right, it can be rewritable, right? Maybe a few million times.
Oh, okay.
Yeah.
All right. Any more question? Ada soalan lagi tak? It's a very menarik topic.
Okay, so if no question, I have a final how to say urge, right? So and how to say, all of you are welcome to venture into RFID, right? You can see that, right? we can actually I5d, right? It's very easy to get industry funding. I work with a lot of industry players, right? From overseas, from Japan, from Taiwan, from Hong Kong, from Singapore, even from China. I can get external fund very easily because these are really practical. They are really in practical application.
I contact you, Prof, because I also have something in my mind about the RFID project. I'll contact you personally after this. Oh, we have one more question. Okay, from Dr. Nuruhuda. Prof, do you accept one more question?
Sure. Anytime. Come.
Okay. Dr. Nuruhuda asks, do you take special measure to ensure that the RFID tag is weatherproof or can it be operated during wet condition?
Yes, actually, right, for such a tag, right, and how to say, it is laminated. This one, right, for example, after we put it, right, and put the chip, right, we laminate it with another very thin PET layer to protect it. And of course, right, for raining, right, I think for wet condition, it's okay. If you stay there, right, if you want to put it under rain, right, I think you know, right, because raining is also very attenuative. I believe that, right, it will affect the re-range quite a bit. And of course, right, but I think the key point is not raining, is temperature.
All right.
Because for this bond, basically, right, I think you have to take care of the temperature. If you really want to use it, right, beyond 200 Celsius, right, you have to use a special bonding material. Otherwise, right, the chip will just fall off.
Okay. Thank you, Prof. Last question from Associate Professor Dr. Chang. Hi,
No problem.
Prof. Do you apply RFID in medical diagnosis?
Yeah, I do. Actually, right, I also design RFID, right, using some fabric material, and it's how to say, it also has been commercialized. I hope that you have never done that, right? If you stay at somewhere hospital before, somewhere medical center before, right, all the text on the closest, on their how to say, on the pillow, on the how to say, blanket, they were designed by my group.
All right, like for inventory checking or something, isn't it?
Yeah. So that in some way, right, let's say, right, for a blanket, it can be used in which floor, by which patient, how many times. Actually, all of this how to say, are recorded automatically.
Okay.
Yeah.
There's a lot of applications for it.
Yeah, even the mattress cover, right, they have a tag. The tag is designed using a fabric material. Actually, it was designed by my group.
Okay. So it can be washable.
It's washable. It's washable a few thousand times.
Oh, okay, Dr. Chang. Dr. Chang would like to add, perhaps COVID virus can be detected rapidly using RFID in future within short while.
For COVID-19, you want to record using RFID, right? Possible.
Maybe Dr. Chang can discuss more with Professor, with Prof after this.
Yeah, anytime, right?
Any more questions? I think very hot topic today. All the audience are very active. Yeah.
Actually, my group, right, we are not only collaborating with industry. You can see that, right, we are also publishing in the IEEE transactions quite frequently. We are very active in both publication and also we are working with industry.
Wow, good. Okay, any more question? I think soalan lagi tak? Any more question? Oh, okay. I think there is no more questions, Prof.
Sure.
All right. Prof, have any last word to say to to audience? Any last word for them?
Finally, right, thanks for attending my talk. Thanks for your time, right? You are welcome to venture into this RFID world, right? If you want to venture into this RFID world, welcome to contact me anytime.
All right. Thank you very much, Prof, for spending your time to be here today. It's a very nice presentation. On behalf of our School of Computer and Communications, as well as ACE, I would like to say thank you, everybody, for attending our webinar today. And don't forget to register your attendance and also to fill up the evaluation form so that we can improve our webinar in the next sessions. So with that, thank you so much and Assalamualaikum. Jumpa lagi.
Okay.
Thank you,
Thank you.
Prof.
Bye-bye.
Bye-bye.
Hello.